students, today we shall study regarding the infrared spectroscopy. This is the actual infrared spectrometer. So we shall study now what is infrared spectroscopy. It deals with the interaction of infrared radiation with the matter. It can provide wealth of informations about chemical nature and molecular structure of the compound. Usually, the spectrum is obtained by the absorption of IR radiation by the organic molecules. Hence, it is widely used for the analysis of organic compounds and also some of the inorganic compounds. In IR spectroscopy, the electromagnetic radiation corresponding to IR radiation is used, and it interacts with the molecule and causes the molecular vibration. Hence, this part of the spectroscopy is called as IR spectroscopy or infrared spectroscopy. Here, the region corresponding to 0.8 to 2.5 micrometer is called as near infrared range. Then 2.5 to 50 micrometer is called as mid-infrared range, and 50 to 1000 micrometer is called as far infrared range. These are the values given in terms of wavelength. At the same time, here the values are expressed in terms of wave number. The absorbed IR radiation will cause the vibrations in a molecule. That means when we say a covalent band between two atoms is of a certain length, we are citing an average length because the bond behaves as if it was vibrating spring connecting the two atoms. For simple diatomic molecule, this model is easy to visualize. So when a covalent bond oscillates, due to the oscillation of the dipole of the molecule, an electromagnetic field is produced. Greater the dipole moment change, then intense will be the electromagnetic field that is generated. When it interacts with IR radiation, the frequency corresponding to the frequency of vibration of the diatomic molecule will couple and its intensity will increase. And that particular frequency will be absorbed by the molecule. That is why in the infrared spectra, usually the graphs are plotted against percentage transmittance on the y-axis and wave number along the x-axis. Hence, the dips are produced in the spectrum and they are called as bands or peaks in the IR spectra. This is a typical IR spectra where the top presents 100% transmittance and bottom 0% transmittance, and the wave numbers are plotted along the x-axis. A number of peaks in the inverted position are obtained because the molecule absorbs IR radiation, and this absorption will decrease the transmittance, and greater the absorption, then the intensity of the peak will increase. And this absorption of radiation by the molecule is governed by Hooke's law because the vibrating diatomic molecule can be visualized as a simple harmonic oscillator, and the Hooke's law can be applied for that simple harmonic motion. According to this law, frequency is equal to 1 upon 2 pi into square root of k by m, where k is the force constant, or it also refers to the strength of the bond, and m is the reduced mass, where m1 and m2 are the atomic masses confined to a particular bond. M1 into m2 divided by m1 plus m2 is called as the reduced mass. As the force constant increases, as the strength of the bond increases, the wave number absorbed will increase. Similarly, as the mu reduced mass increases, there is a decrease in the frequency. You can see here, in case of triple bond, double bond and single bond, the strength of the bond increases from triple bond to the strength will be more for triple bond to double bond, hence the wave number absorbed will also increase. Similarly, as the atomic mass increases, there is a decrease in the frequency. So how the mass influence vibration of a diatomic molecule can be visualized with this picture. Greater the mass, lower the wave number. So in case of the diatomic molecule, usually the molecules will reside in the lowest energy level. When they absorb radiation, they excite to the higher level, namely V is equal to 1. According to the Bohr's principle, E1 minus E0 is equal to h nu. That is, the energy difference corresponding to the particular frequency will be absorbed by the molecule, and the higher energy levels usually they are called as overtones, and they are not uh, studied in the basic IR spectroscopy. So here it is possible to calculate either force constant or the reduced mass with the help of this formula, provided all the informations are given. So in the infrared spectra, we will study these aspects, namely position of the peak will tell regarding the mass of the atom and also strength of the bond. Then the intensity of the peak shows the polarity of the bond, and the width of the peak shows whether there is a formation of hydrogen bonding in a molecule. So when the molecule absorbs IR radiation, then it can undergo two types of vibrations, namely stretching vibration and bending vibration. Stretching vibration means there is a change in the bond length with respect to two atoms, and in bending vibration there is no change in the bond length, but there is a change in the bond angle. Hence, in stretching vibration again there is a symmetric vibration and asymmetric vibration. Then in bending vibration there are two in-plane bending vibrations, scissoring and rocking. Then there are two out-of-plane bending vibrations, wagging and twisting. In case of symmetric vibration, you can see here there is a change in the bond length and there is no change in the bond angle. In symmetric vibration, both atoms will move at a time, and in asymmetric vibration, they will move unevenly. In bending vibration, in plane bending vibrations, scissoring and rocking. In scissoring, the two atoms will come near at a time, and in rocking, both will move on the same side. Both these types of bending vibrations are in plane, means they occur in the same plane. And there are two out of plane bending modes, wagging and twisting. In wagging, both atoms will move simultaneously on out of the plane, but here they move oppositely. So with this, I will conclude this lecture, and the remaining I will tell you in the next class.